I'm the token New York Times guy at this event, but we do use Cassandra, and I'm going to talk a bit about that and about this project that I'm working on. We're Python users primarily. Got any Python? There must be one over there. Yeah, okay, so I'll try not to be too boring to the Java guys. That's I remember I've been in computing a long time, and this is actually my 50th year of working in computing. And I remember when Java came out, and it was fun, you know. But I've moved on. And so my project is the fabric, and this is a little graph that I had fun creating one afternoon. And people ask, you know, why is the funny bee in the middle? And the funny bee is in the middle because my boss was Russian at the time. And this was a extracurricular project, and I had to talk him into supporting it. So fabrika is a Russian word, fabrik is German. And he liked the Russian bee, and that gave me everything I needed to steal the time to work on it. What we tried to do with thinking about fabric was to kind of start with a new slate at the Times and think about how we wanted to distribute news and how we wanted to gather analytics, and in particular to see if we could build a platform from the ground up that would be radically simpler than the enormous hodgepodge of stuff that we have, because we're an old company, and old company in the tech space might be 5 years. You know, we're considerably older than that, and we have a lot of those vestiges of ancient technologies from linotype to you name it. So, and they all show up in our systems, and they all show up in one way or another in the stuff that we have to maintain. So could we really make it simple? Could we really make it flat? And could we really make it global all at the same time? And I think of our systems as we're trying to build a system for the 99%. You know, there's the Googles and there's Facebook and those guys, but we aren't those guys. We don't have the money and we don't have the manpower to do that. So could we take all the good work that they've done and just think about ways to simplify it in something that we could afford to run and that would meet our needs for reliability and global reach? So we started to think first really about communications and building a communications matrix. And so I think of it as matrix, that the fabric is primarily this communications matrix that extends through data centers around the world that we need to support our communications. And as we thought about, because we're working on the DevOps side too, so we're going to build the infrastructure, the application, everything all from the ground up. This, by the way, when I say we, I'm talking about me and my partner. So it's not a big crew. So we thought, well, what if we just sort of scatter nodes out of there? These are small nodes, and we're going to just spread them through this matrix. And what we want to do is come up with a way for them to self-organize and to register their capabilities, because they have different capabilities. Typically, you know, we run 2 or 3 different sizes of nodes. Just along the simplification line, we run with like 1 AMI. We do run in Amazon, by the way. And all of them make use of a small set of software. and then they are distinguished by their roles, and then they take on a personality, if you will. So we refer to them as stem cells, and they evolve into their personality, and they connect up. And then everything connects to them. So all of our systems, all of our users, all connect to the fabric. And they don't connect through intermediaries, they connect directly to the fabric. So how do we do that? And well, first we spread the fabric across multiple regions. Right now we're actually in production in Oregon, Dublin. We've got like a toehold in Tokyo. Probably Sao Paulo will be next, Australia. Pretty much we're using the Amazon cloud to project low latency wherever we need to. When users connect, they connect using least latency. And actually we have a second layer below that where we can redirect. And we do this because I kind of think that there's like a big wheel, and the operations guys like this. And if they twist the wheel to the left, everybody goes to work. And we can shift our load, and we can A/B split it by basically using a combination of least latency and weighted routing and adjusting the parameters in real time. So reason we do this with health checking, by the way, is because it really takes care of the problem for us of failing zone or failing region. We had a good test of this just a couple months ago. Really, the computing problems, networking problems, are not the big problems we run into. We run the same problems you run into, which is people make mistakes. And we had one of our team, my team's grown to 3 by now, and he introduced a bug, a little bit of buggy code into Oregon. And it ended up, because things are tightly connected, bringing down every node in Oregon. All the Cassandra nodes, all the core nodes, all of our product nodes, and all of our gateways. What happened is that all the connections shifted to the other regions. And the end result was that nobody noticed. We noticed, of course, and it took us a couple hours to get everything back, but nobody else noticed because we auto-scaled and it took the load immediately. Of course, there are zones. We spread everything out across those zones pretty evenly. We auto-scale the gateway nodes. And just to dive down into a zone, this is kind of what it looks like, or into a region. This is really just a subset, and I'm not going to go through what these things are, but just to give you an idea of the connections and the potential connections. So they all, where it says it's a potential connection, it means that if for any reason the connection fails, it will switch over to one of the potential connections. And those, like the core you see, the yellow ones and the orange ones in there, we're actually, you're seeing one layer there, there are actually multiple layers there. And every layer has its own set of connections. So we run with a lot of connections throughout, and that's why I like to think of it as a mesh, because after I made this diagram, I said, I'm not going to make any more of these, too many lines. So just to go over kind of a real overview then, and I think of it as a global mesh with memory. And we need a memory for certain kinds of operations. Users have preferences when they log in. We want to retrieve those very quickly. We use the memory for that. The memory is Cassandra. If users aren't logged in, and we send them a message, we want them to get it as soon as they log in. Okay, so we use Cassandra for that. When we want to process analytics, we need a place to put stuff. Now, we're a platform, so we don't actually do much analytics processing ourselves. Instead, we'll say, hey, we'll give you a cluster. And we'll just send it to them, and our BI, Business Intelligence Group, can work with it. So that's not our issue. But we do have millions of users. I'm going to show you a graph later to kind of give you an idea of the variation. But we may run from 100,000, 50 to 100,000 users at the low point of the day to a couple million users at the high point of the day. So we're scaling up and down. We're always adding and subtracting machines to do that. We really only speak WebSocket, AMQP. SockJS is a transition protocol for us that makes use of XHR streaming and so forth and so on to emulate a WebSocket interface. So we can support virtually every browser, every device that connects to us for the news. Get this up in here. We picked up some stuff that's similar to Cassandra. It's interesting, to me anyway, from a messaging background, which is that important things are replicated. We replicate our messages and we let them race to resolution. So for example, if there's breaking news, then that gets injected at one point into the fabric. The first thing we do is replicate that to every region and zone. We process it in parallel, and then we resolve, then we exchange and resolve the duplicates and try to send only a single copy to consumer. We then resolve at multiple layers. Typically they only get one, but it's a messaging system. They may get a duplicate. That's okay in our system. The whole mesh tends to resolve in about a second globally. So it's pretty fast, at least so far in our use of it. We give back a message ID that's been generated by our major producers so that they can check, they can do an end-to-end check to see that everything got there. When in doubt, they resend. If you get disconnected, reconnect, and we'll redirect you to something live. I'm not going to go into it today, but our WebSocket server is, I'm really proud of that. We currently support about 100,000 connections per machine with absolutely flat connection times, tens of milliseconds. It's Python with a C coprocessor bolted on. It's really fast. And that's running on a small machine. That's on a C1 medium running in the web. We think we can go substantially higher than that, but actually we'll stay with small machines. And I've been really impressed here at Cassandra at the size of machines and the things people, we try to stay small. So we're trying to run Cassandra on the smallest machines we can. And so we try to wring everything we can out of it, and that kind of brings me to the Python stuff. Okay, so this is, I took a snapshot this morning. It's just to kind of see what yesterday looked like, and you see that big ugly spike there in the middle? That's what a breaking news alert looks like. Okay, and if you're familiar at all with RabbitMQ, which is what we use for our message broker, then you can see these rabbits are just loafing here. And we like to keep the rabbits loafing because we're using clusters. The cluster needs to be able to talk. The cluster in the RabbitMQ world is different from a Cassandra cluster in that consistency is at the top of the list. And so they need to be chatting with each other all the time. So the other thing we do is we do everything in memory. We never persist. And the reason we don't ever have to persist in our message brokers is because we use Cassandra for that. So we've really separated the problem in a way that takes advantage of both of these platforms. Okay, so we do messages, and we have a very simple data model. This is actually a little too simple, but pretty much our message is some metadata and a blob. We don't care what's in the blob because we're a platform, so we just push blobs around. We do care about the metadata, and in fact, we have a very nice cube, as was discussed in the previous one, of about 8 items that we use on our metadata. So we track everything by product, by project, so we can do internal accounting and keep track of our users that way and provide them with nice reports and so forth about it. So that's what a message looks like, and that's, of course, a Cassandra version of a message. This is what a message looks like in the Rabbit. And you can see how the metadata is kind of migrated down there into the headers. And then some of those items have been promoted in a way that is useful for the Rabbit up into the properties. Okay, so the idea is that the message structure is general enough that we can represent it in Amazon S3, we can represent it in a lot of different environments. This is useful for us because we're dealing with people that use Java, PHP, Go, all kinds of consumers that need to come in either via WebSocket or MQP. So let's think a little bit then about these benchmarks I'm going to tell you about. So I've got some timelines, the Rabbit, the client, Cassandra. Of course, there's more than one Rabbit, there's more than one client, and there's more than one Cassandra, but we're going to simplify a little bit. And this is a pretty simple diagram of how the benchmarks work. The client subscribes to the message broker, okay, gets an event, which has data, a message, and then does something with Cassandra. Cassandra acknowledges it, and we acknowledge back to the Rabbit. So that would be a synchronous approach, right? And in my push benchmarks, this is kind of what they look like. And what I've done in my benchmark code is I modeled our actual environment, and I'm using clusters that are like my actual clusters in production so that I could get a good sense of what things look like. Now the poll is a little bit different, and because there's more data coming back, so I would expect that it would be slower because I'm retrieving, I'm not sure, I want to look at the benchmark. And B, there's a lot more processing that has to occur because I have to marshal and demarshal those messages. Okay? So that's synchronous. So I could do that with Thrift, or I could do that with the native interface. But if I start to add concurrency, then I have to go asynchronous. Okay? So we're using SQL Native. Now we use the libev event loop, and actually that's a lot of what I do is to write the drivers. So I wrote the driver to Rabbit and got it to work together with the driver to Cassandra. So I don't know if you've ever worked with an event loop like libev, but it's like having a wild animal in a cage, and you feed raw meat in one end, stand back, and it spits it out the other end. It's really fast, but it's not that easy to control. And when you have 2 of them running and you're trying to run them asynchronously together, you can run into problems. And so Tyler Hobbs and I have gone back and forth a little bit and making the changes to both drivers that actually made that possible. So this is a concurrency, degree 3, okay, so we're getting some overlap in processing. That's really the key thing to note. But we're doing it through event processing. We're not using threads here, okay? And we're getting more concurrency. Now this is a little misleading because all those arrows are so neat. In fact, the order of things is not determinate, okay? And they will come back in orders that you don't expect. They will all eventually come back, okay? So that means you have to kind of keep track, and the driver helps you do that. So let's build a message. This is just some simple code, my Python code to build a message. And it creates messages which has roughly the dimensions that are typical of our application. And then when you push it, you just keep pushing it in the pipeline, right? We've got a pipeline going out, we've got a pipeline coming back. So I'm going to push it to my level of concurrency. Then I'm done, and then basically this program waits around until something happens. The thing that happens is that something comes back in the pipeline. Okay? So I built a message and I've submitted the query. What's an actual query submittal look like? And this is it. I grab the body and I do an execute async in Python. Okay? And then I add my callbacks. So my callback is where I'm going to get something back. Now you notice that I pushed my limit of concurrency into the pipeline. So now, every time one comes back, all I need to do is, am I done yet? If not, push another one. If I'm done, then finish. Okay, so that's it. This is basically how it works. I run a 50 in the pipeline all the time until it winds down at the end. So that's an example of concurrent programming. So let's look at the push. This is my disappointing first graph of performance. And what's wrong with this picture? What's really wrong is I didn't use DC aware. Okay, we're running with 6 nodes in Dublin and 6 nodes in Oregon. And the 170 milliseconds of round trip latency there is not good for your performance when you are running with small levels of concurrency. But let's see what it looks like as we add more concurrency. And I really like this graph because it fulfills my expectations of queuing theory. And what I'm really talking about is as we increase concurrency, DC awareness becomes much less important. And that's because I'm filling up the pipeline between Dublin and Oregon. And so therefore, DC awareness is less important. And what that is, the interesting takeaway from there, which I'm still thinking about, is if I have a point source that's really emitting a lot of data, maybe I want to turn DC awareness off and let it go to every node in all my regions to spread out the work. Because DC awareness is not that important. If I'm throughput oriented, then of course if I'm latency oriented, I'm out of luck. I really want to stick with the DC awareness. Okay, so that was kind of interesting doing these benchmarks. But let's look at a little more detail here. And I'm going to be relatively quick going through these, I think. But basically we're looking at how many workers. Now this Python program will multiprocess to any degree. And so that's how I'm doing this, and it'll also take levels of concurrency. I'll show you a little bit later. And so as I add workers now, there are a couple things to look at here. Concurrency's down at the bottom. I'm doing local quorum because I found that that's how we run, and there wasn't that much difference between concurrency level 1 and local quorum in my benchmarks, so I focused on that. The percentages are interesting because I'm running on an 8-way processor here. It's C1 extra large. And so So there's a limit to how much I can allow any one of my services to take. And it's probably around 400% of the 800% that's available. Okay? So, and you see an interesting break in there. Okay, so, and now I'm starting to lose because the process is getting inefficient here, and or I'm hitting other things. I might be hitting memory, or in my clusters, actually I peaked at my cluster. The cluster's getting close to being overdriven at this point. Okay, that's 8. And this is what they all look together. And basically, when you look at something like this, and this can tell me, hey, I like these ones where the slopes are rising rapidly. That's kind of where I want to be, one of these guys up here. But it's also got to end well. And these top 4, they don't really end that well. So those ranges, those are indications that I only ran 3 iterations here, but those are the high and the low and the median. So of those, I would say for push in particular, I'd probably pick number 4, because most of the time, and I'd probably operate it with concurrency up around 100 or 120. Most of the time, I would expect it would be operating in this range. The benchmark's tailored to our environment. So these are bursts of like 22,000 messages. When I get a burst, it'd be okay for it to go ahead and rise up the graph. At that rate, we're talking only under 10 seconds of processing to take a burst. That would be, a burst like that would be typical of what I get back on a breaking news. Okay? So I'm really, I guess the message here is tailoring to your environment's important. This benchmark's really tailored for us. This is the Python program. It's got a bunch of, you can pretty much play with everything. How many remote DC hosts, prefetch. Prefetch is the concurrency. How many workers, whether it's DC aware, whether it's token aware. I didn't talk about token awareness. I haven't found any benefit to token awareness. And I don't know whether it's my code or the driver code, and I'm going to have to dig into that a little more deeply to figure out just why. We're running replication factor 3 on 6 nodes in each region, so it could just be that the additional overhead is overcoming any benefit. The additional overhead, and you look in the driver, and it's got to like jump around a little bit to figure out which machine to go to. So maybe that's just it. And actually, when I push run these trials, then there's a supervisor program that runs all the stuff. Just to give you an idea, this is kind of what they look like when they're running, So he's building up his 22,000 messages and then runs it. If you look at the unacknowledged there, unacknowledged in rabbit terms means that's my concurrency. So I'm running with overall concurrency of 3. I've only got 1 process running, 1 consumer. If I look at one of the later trials, I'm running with 165, 3 consumers. So that's a concurrency level of 55 per sub-process. Okay? Now, in Python, these are not particularly expensive in terms of memory. We're talking about 30 megabytes for each sub-process that you run. So it's not expensive that way. You have to be careful about how much CPU is being consumed overall to stay in an efficiency. Okay, the polls are similar, except there's a lot more data, so I would expect my graphs to be flatter. And the reason they're flatter is that I'm using a lot more CPU to accomplish each, and I just run out of CPU much more rapidly and don't get near the throughput, but still pretty good throughput. So my overall graphs look like this, a lot flatter. So this helps me with my planning. Do get bursts that are looking for reads. They're nowhere near as much or as common as the bursts that we get of pushes. Where I get a burst, like this will be when a WebSocket gateway node typically goes down. If it goes down, all of its clients have to move at once. They all will be looking for their information out of Cassandra at the same time. And so I may get a burst that'll last, a while. So we're measuring one process here. We're always, one guy here. Each of our cores is going to be running at least 3 of these. We may be running multiple cores in each region, so they aggregate linearly, so we can plan for capacity of many thousands. We're not actually anywhere close to that yet. As an infrastructure provider, it's kind of my job to stay ahead, and I'm trying to stay ahead by an order of magnitude to 2 orders of magnitude over my internal groups, because they turn around to me and they say, can you do this next week? And I want to be able to say, sure, all I need to do is triple the budget, add the nodes, and we're ready to go. So that's kind of the overview of the fabric and a little bit of the work that I did on Cassandra, where when we started with Cassandra 2, which was in January, we went into production with it. I was pretty conservative about using the Python driver because I think it was brand new at that time. And so we've been running completely in synchronous mode with the Cassandra driver. But now with these benchmarks and so on, I'm pretty confident that we can run with asynchronous, and it's going to increase our capacity by a substantial amount over the same hardware. That's it. Anybody got any questions?